See a red light. So I hope I'm recording. Hi boys and girls, it's me Butch. My name is Terry David Silvercloud. I'm 74 years old. Today is the 22nd of November 2018 in Vancouver, BC. It's cool, gray and rainy, just after 3 p.m. in the afternoon. And where do I want to go? Let's just jump into it. This is my third attempt at trying to pull a video together about unified particles and how the universe is constructed. And it turns out it's not easy to do in a hurry, and I have no idea why my voice is so hoarse. But I'm going to carry on. So where are we going to begin? I want you to imagine that where I'm sitting right here is the center of the universe. Where you're sitting is the center of your universe. But for me today, for everything I'm going to talk about, this is the center of the universe. And the universe is infinite. I'm not going to go on to why it is or anything like that. So the universe is infinite, and I want you to imagine that the universe is full of water or any kind of liquid you can think of, as long as it's a liquid. Solids, it's just easier as a liquid, and I don't have time to waste on why that is. So pretend the universe is full of liquid. There's no air, empty space anywhere, and no arguments about what's dissolved in the water. Of course there's stuff dissolved in the water. That's the point of it being a liquid. There's all kinds of stuff in the air right here that we don't see, and we are breathing in every moment particles, actual physical particles. When I go suck air in, I just sucked in dust, which is probably dead skin and God knows what. I have a fairly clean place, but I'm an artist, old and lazy. So you know how dust accumulates. The point I'm trying to make is a dust is a solid thing, and for the rest of the talk, solids are either fermions or baryons, and baryons are the three major baryons are electrons, protons, and neutrons. And there are other particle kind of things, and we know bits about them, not everything about them, such as neutrinos, and a neutrino is a good example, and there are three distinct types, and I'll try to remember to explain why that is, which conforms perfectly with my theories. Everything we're talking about here is my theories, my ideas, and I'm doing my very best to make everything I say conform with all known physics and to obey all known physical laws. I'm not breaking any laws anywhere of physics or of known science or of mathematics even. I'm a lazy person. I don't like mathematics. I don't like tedious things. I'm an artist in my old age, and I'm 74, so I could be dead tomorrow. And since I can't spread papers on science, and I got my YouTube channel, so I'll just tell you people my ideas, and some bright young person out there may say, oh, I get it, and run with it, because I know that this is a very good concept. So where were I? So particles can be big or small, and it depends on your size. I don't have time to waste like I did in the other videos about talking about why your size affects how you see time. But when you're really, really tiny, you have to realize that your wristwatch is running in picometers or attometers, or you may be living in a world where your time frame is 1 second times 10 to the minus 50. That's a lot of zeros, isn't it? So we don't know quite where zero is, but I have an assumption it's somewhere around 10 to the minus 33 1/3. That's my guess. That's just about where zeroness will happen in any reality, no matter how small you are. But in really tiny realities, a second is a really long time, and for them, they are essentially already traveling at the speed of light in their world, in their time frame. And unless they're united, unless they're unified particles of a certain size, and that size has to be, it would appear larger than 1 micron, they don't know heat. They're already frozen. In their world, they have their own version of solids, liquids, and gases in really small sizes. And all that world, I'm telling you, is dark matter. And the forces between the particulate at that extremely small level of reality is dark energy. But like all things, things run in numbers, and even when you have an infinite universe where there is no end to numbers, there are some numbers which seem not to have endings, such as pi, and the square root of 2 gets to be really long. The point I'm trying to make is there are ways of dividing up a decimal number system to seemingly infinitely small parts. That's a good thing. So every now and then you reach a barrier in size, clumping as it were. You won't really notice the dust particles that you're breathing in right now and I'm breathing in, but if you're in a sandstorm, suddenly the dust particles are getting really big and they're clogging up your airwaves and schmucking up your eyes. So imagine you are on a spaceship the size of one of those dust particles. You'd be dodging rocks the size of your spaceship. You're in serious trouble and you'll probably be dead shortly. There's probably no escape, and that's a good thing. So all these collisions involve forces coming together in different ways, and forces will always resolve themselves, because from the first law of thermodynamics we know that energy is never going to totally be lost. It's just going to do some shifties. And in the second law of thermodynamics we can take from that is all particulate must decay. It has no choice. Sooner or later you're going to come apart. You're going to meet somebody bigger than you, or the forces that hold you together ain't going to work no more, and you're going to reduce yourself to whatever you started with. So we have an infinite universe full of water. This water is made of somethingness, and until we encounter anything that we can visually see or bump against, we don't recognize anything there, and that is dark matter in our electronic universe. This is important. This is my idea. The electron is the smallest stable particle of which we know, and it's seemingly indestructible. I'm telling you that it can be destroyed, and it'll turn into either 10 or 20 gamma particles. I'm still working that one in my head, but the smallest particle in our material world that will cause us any issue is a gamma particle. And a gamma particle is tetrahedral in shape. The thing you need to know about tetrahedrons, without me wasting a lot of time, is they come in all kinds of shapes. Anything that has the least number of vertices, the pointy parts, faces and edges, anything that is like this that has 1, 2, 3, 4 faces, 1, 2, 3, 4 pointy parts, and 1, 2, 3, 4, 5, 6, did I get that right? 6 edges is a tetrahedron. So there are tetrahedra and there are tetrahedra. They come in all shapes and sizes, and they are a foundational mathematical induced shape. Mathematics dictates it. You can't have a three-dimensional shape without at least that many pointy parts, faces, and edges. But they can come in different sizes, and they can come in different arrangements of the way they do that. When we're looking for the smallest of the small, the first thing we must dismiss is spheres. Did I say that right? Balls. Got to dismiss the balls. The reason for that is to qualify to be a sphere, you need theoretically an infinite number of pointy parts. So we don't want to look for spheres. That just involves far too many pointy parts. But I'm going to tell you, this is my opinion, that having stellations, such as this candle holder, can you see it there? See if I can get you real close. If something has this kind of physical shape, you will perceive it to be a solid. And if you look at this quartz crystal, see how naturally it just came out to be a cuboid? It has pointy parts and flat sides. Nature did that. Nobody else but nature did that. It just happens. You have to accept that there are barriers in the world, and they're ruled by the possibilities of numbers, and mathematicians would love to spend hours talking to you about all kinds of number theories and how numbers affect our lives. Where we're at. So particles at some point reach a threshold where you notice them, and where you notice them will depend on how big you are. It'll also depend upon how you receive all information which you receive. And all information which we receive electronically is light, and physically sound, and physically what we would call gravity, where you seem to be, something is holding you down in the earth, and I'm telling you that all things are trying to come to rest. The moment anything comes together, particulate, it starts obeying the second law of thermodynamics, and it tries to come apart. And the bigger things push the smaller things. Objects in this liquid universe of ours, I'm telling you, must obey all the laws of buoyancy and all the laws of flotation, where there is no up nor down, and up and down is determined by how much spin you have. So the spin determines poles, and the pole is your relative up and down. There is no such thing as a true up nor down. I remember back a while ago, I hope to tell you, imagine I'm at the center of the universe, and I'm going to divide the entire universe in half forever. I'm going to make a flat plane. Doesn't matter which direction I do it, but I'm going to make it this way because that's the way this board is facing. It just makes it easier. And I don't want to drift too far on my train of thought. And I don't want to spend forever talking about this. So we want to go down to the very smallest of the small. I'm going to do this like my computer's over there. Let's see, I'm going to get you there. Now you can see this is an X here. This is an X, and I've joined right here. I'll make sure you can see this. I think you're on the screen. I just drew a line from corner to corner of a perfect square, and I just picked this perfect. Remember, I divided the universe in half. Half the universe is over there, the other half forever is that way, and it goes forever below me and above me. And I sliced out a square out of it. And I sliced out the very smallest one that I could possibly do in my size world, which is near nothingness. You have to accept there may be smaller ones. There's always smaller ones, or there could be. Now, for the sake of this discussion, I'm going to number these lines here, which form these right-angled triangles, as a value of 1. That dictates that because these are right-angled triangles, that the length of this line has to be the square root of 2. We don't know how big this is, but we want to have easy numbers in the decimal system that can have ratios. Now, if I were to fold this all up, it would form an octahedron. And the octahedron would be composed, you can see, of 1, 2, 3, 4, 5, 6, 7, 8 right-angled tetrahedra on one side. And if you did it the other way, 8 more on the other side, so it would be a total of 16. Did I get that right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 8, and you get your Egyptian-style pyramid. The universe wants to make different shapes, and this is one of the shapes it'll make. Now, the interesting thing about if all these little right-angled tetrahedra got themselves together and formed themselves, this object is still, it's not really anything except forces at that particular point. The forces of the universe are coming on every one of these faces all around it, and this bubble of near nothingness has formed itself into a bubble bigger than the basic right angle tetrahedra, which we're trying to do exactly the same thing and in the end they form this shape, which as a bubble can now have spin, and once it gets spin, now it has gained more energy than it had when it was still. That energy was stolen from the rest of the universe. Now the rest of the universe has to fracture and shrink. Somebody's got to make up for that energy. And what's getting out of the way is all the dust in the air of the smaller dark matter that is there. It's just air. It's so small, it doesn't matter to this shape. The original tetrahedra somehow grew. The individual ones that made up the parts of the octahedron grew, and because you always start with a triangle, usually, they will just start building up and build new pyramids. They will start to stellate. Remember the stellations? Remember this thing? It will begin to stellate on its own. And at some point, or it may encounter others, it may encounter something with which it could live. And here's something else with which it could live. Here is a really giant shape, but it's still the right angle tetrahedron that's grown to be really big. And I don't have time to waste about why it might do that. It's just possible. And what's really interesting is if we took this octahedron, I'm not going to waste time trying to tape it back together. We could take several of these and put it inside of these right angle tetrahedra could form a net. It's called a net, I believe. I have to ask the mathematicians. I'm not a mathematician. I don't like math. It's too tedious. But they could form a net around that octahedron, and in this case, the vertice of that right angle triangle, and if you want to go and check it out, you'll find this works. The vertices on that right angle triangle, are you there in the screen? Have the value of 2. Remember the value of 1 on the other octahedron that's being netted? This has the value of 2, and the diagonal here has to have the value of the square root of 8. Is that right? Did I get that right? Yeah, so it has to be 2 times 2 is 4, 2 times 4, 4 plus 4, sum of the squares on the other two sides. So this has to have a value of the square root of 8, and you could keep building bigger and bigger and bigger things which will just keep going up. The next one will probably be 4. Now I want to divert from that a bit, because one of the ways of trying to figure out what on earth the universe is doing, if you get even bigger, well, that's what I want to show you before I get away from there. When we were talking about, let me get in the screen here. See this sucker here? There is a cube around a larger tetrahedron, and inside every tetrahedron there is an octahedron, and inside every cube there is an octahedron. You can start monkeying around with these basic shapes where one builds upon the other continuously, and I really want to show you the Merkaba star, which I'm sure is here somewhere. I thought I had this all ready to go, and of course I don't. I got my back to you. Once you get a cube, where are you there? Once you get a cube, there's a variety of things you can do. This is an octahedron with tetrahedra on the corner. You can see they can easily be enclosed by a cube. Here are 2 tetrahedra. This will all be very familiar to Jewish people. You start from what to you is so small that it's not matter. But with the right combination of forces, the basic shapes of reality, which are really the tetrahedron, and fundamentally, because remember back at the beginning of that, the smallest little piece we just sliced out of the wall of the universe there, you have an Egyptian-style pyramid, and on the other side of the wall, you have the other Egyptian pyramid. The square is the base, which is right on the wall between this side of infinity and the other side of infinity. And with those right-angle tetrahedra, we should just assume that the right-angle tetrahedra is the strongest tetrahedron. You can... I had something I was supposed to be telling you and I can't remember, which is why I made this. Well, this again, remember I was talking about how you can, once you've gained a base, you can start multiplying on this value of 2 to the square root of 8, and the next size up would have a base of the square root of 8. And you could do the same thing with a tetrahedron with a square root of 8, just for tiling purposes, which is where you get these Merkaba star-shaped things. And inside every tetrahedron, you still come back to the octahedron. These are the surfaces of the octahedron inside any regular tetrahedron. The world just expands outwards and the objects keep getting larger. Larger things push the smaller things. So if you're at the center of anything, you have to be the smallest thing. And the smallest thing that is really stable is either a dual tetrahedron or, better yet, dual right-angle tetrahedra. 2 of these back to each would be quite strong. This is a very strong angle here. It's the least likely to have to obey the second law of thermodynamics. If it were taller, even if it was, it would be forced to decay. It just, because this 45-degree angle here divides the pressures equally all the way down, where any other angle doesn't. So something has to give somewhere, unless you can always divide the pressure equally one side to the other. I don't want to make this a really long video, and I'm probably missed all kinds of things I wanted to talk about. So we want to, at some point, there's a threshold in the sizes of things. Am I in your picture? I guess I'm supposed to be sitting down. Watch me wreck my stuff here. I forget the camera's not seeing everything there. So there's a threshold at some point where, from our point of view, matter begins. And I've told you it starts with the gamma particle, which I'm telling you is tetrahedral. And it might be a dual tetrahedron, and I'm still working that out, but it doesn't really matter because half of a dual tetrahedron is a tetrahedron. And we want to quantify the universe. All you quantum physicists want to do that. So I'm going to tell you, for my purposes, the best dual tetrahedron would be two right angle tetrahedra back to each. Here's a right angle tetrahedron, so 2 of them, because then it can spin, and once it's got spin, it can gain energy. Like, spin is energy. Energy is work being done, or it's the ability to do work. So once something starts spinning, it's gaining energy, and energy is not free. There's, even if I say the universe is infinite, infinite is a long way away, and you just simply steal it from your neighbor. You know, you do a Simpsons and you plug the extension in Flanders Place. You got to get the energy from somewhere. You can't run more lights unless you have more power. And spin is a way of increasing your power by spinning faster and faster and faster. Where were I? Oh, so a gamma particle, to me, is a right-angled tetrahedron. But in terms of volume, there's no reason why it could not be the same volume, but in an equilateral or regular tetrahedron. Remember, this is really just fluid. The edges are purely mathematical because there is no empty space anywhere. It's all the same fluid, but these are united particles. They're sharing their forces to fight back the rest of the forces, and that's just the way it works. The raindrops get bigger and bigger, and this is a tiny raindrop and the smallest raindrops. I know it looks very sharp to you, but remember, these things, we can't even see them. They're so small. So they're just the grease of the universe. Where was I? Our universe is run by electrons. We're electronic beings. Sound comes through physical molecules and atoms bumping together. There would be no sound in space. But if we could communicate by radio waves, we can easily do that in space. And that's because space is not empty. It's just full of stuff that's too small for us to see. It's not dark, and it's always solid. Temperature doesn't come into being until things get larger than 1 micron. The wavelength of a heat wave starts around 900 nanometers, and the waves between around 850, it's getting warmish, and when you get up to around 950 nanometers, the electron will say, ouchie, ouchie, you can't do this, I don't want this, I'm out of here. Electrons will come apart, or electrons are holding things together, and if the electrons say, they start spinning faster and faster, and once they start spinning faster than 100,000 times per second, they aren't happy campers at all. So they will eventually turn blue hot, and if they turn blue hot, you can be absolutely certain that whatever they were holding together will fall apart, and now it's on fire. So things that are longer than that don't like... this is one of these barriers I was talking about, that matter starts falling apart if it gets bigger than 1 micron. Speaking of 1 micron, this is a diversion I talked about in the other videos. The rods and cones in your eyes are approximately 1 micron long, and the reason for that is the entire bandwidth of all frequencies of light fall within 1 micron. So a red wave, which is about 0.666 microns, even though it's a very long wave, the entire wave can go into the can strike the nerve, and if it strikes it head on, no matter what it is, this entire thing is going to start shaking, because this is an earthquake wave to it, and that will cause electrons to be emitted from the nerve cell to your brain to tell you you're seeing something. You can only see things at about 10 frames per second. I talked about that yesterday. I don't want to go on about that. Watch one of the other videos. Your brain, unless you're really young or a super athlete, you just cannot process visual information faster than 10 frames per second. That's why animation is always a minimum of 12 frames per second, absolute minimum. And the way they do it when they had film cameras, see, now I'm drifting off. Film cameras were 24 frames per second, so if you were doing animation, you would do 2 frames of every cell, and that would work out to 12 frames per second. And it would be a slightly long duration, because it would actually be 24 frames, but every 2 were the same image coming at you. But if the rate got down to, say, 8 frames a second, you would start seeing jitteriness. So your brain processes information in batches of approximately 10 batches per second. If we look at, I don't know how long I'm running on to, and I got to wrap this up. If we start looking at atomic structure, I'm hoping you can see this. I sort of wrote it down here. If you look at atomic structure, chemists nowadays like to talk about orbitals, but the basic energy levels, there are 7 of them, 1, 2, 3, 4, 5, 6, 7. and the energy levels are labeled K, L, M, N, O, P, and the outer one I'm labeling S because it doesn't really have a name. The other thing you need to know in atomic structure is that level 6 and 7 don't have to be full. So a level 7 can start without level 6 being full. That should be your clue that there are stellations in certain atoms, especially the very, 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 very large ones, and where the radioactivity is occurring, which will be around here, which could hold up to 98 electrons if it wanted to, and doesn't have to, but it's your clue that radioactive atoms have stellations. Now, me being a guy that likes to just look at things and look for relationships and try to see if you're on the screen here. It's also on the board over there. The number of possible electrons for each level, let's not talk about orbitals, but for each energy level are 2, 8, 18, 32, 50, 72, and 98. If you look at the differences between the levels, there's 6, 10, 14, 18, 22, 26. And if you look at the differences between those numbers, it's 4, 4, 4, 4, 4, and the difference between that is 2, 2, 2, 1, 1, 1. It gives you an idea that the structure of all atoms has to be based on either a tetrahedron, 1, 2, 3, or if you counted the one from 0, 4. So it could either be 4, 1, 2, 3, 4, or 3. So different atoms might have a different structure at the center. Some might be based around a tetrahedron, some might be based around an octahedron. And the structure from the center will be some kind of lattice outward from there. I like to think of atoms as being Hoberman spheres. You're going to have to look that up. There's a kid's toy based on this mathematical toy, and you've probably seen it. It's like a ball that you can pull it apart or shrink it. I like to think of the joints of the Hoberman sphere as being paired electrons. Okay, and that when an atom absorbs energy, the way it'll normally react is with spin, but the spin will cause it to inflate to handle the extra energy, the extra photons of energy, and also will cause it to flatten. Our Earth, just for natural reason, has to be slightly flatter at the poles than it is at the equator. It might only be by 1 mile, but the forces of squooshing of the universe are trying to flatten the Earth, and Professor J.W. Gregory noted that if you looked at the continents from the North Pole, it looks like the continents are trying to form themselves into the shape of a tetrahedron, where the apex of the tetrahedron is at the South Pole. And I'm going to tell you, and this is an absolute fact, it's hard to get confirmation, but I can tell you that the Earth and all planets travel through the galaxy South Pole forward. And the Sun is also traveling through the galaxy South Pole forward. And the Sun travels approximately 7 billion kilometers in 1 year. So the Earth actually makes a helix, or one wave, of 7 billion kilometers long, with a period of 365.25 days in 1 year. So the Earth, this idea of the Earth going in circles, that's just all relative in your head. That's why when you start trying to think of dark matter and stuff, I mean, it's happening so fast. It was over with before you thought, what was I thinking about? I mean, it was already over with. As I sit here right here, and as you sit there right there, excuse me, you are traveling at least 400 kilometers per second through space, following the sun. We're always chasing the sun. And the planets, everything's going South Pole forward, and the planets are spread out along the equatorial plane because they're the shock wave of the sun moving through the galaxy. It's exactly the same like the rings on Jupiter. The rings on Jupiter are caused by the shock wave of Jupiter flying South Pole forward through the galaxy. Same thing that happens when you see a jet break the sound barrier. If there's moisture in the air, you'll suddenly see a mushroom cloud around it. And if you see a B-52 bomber because it's built in a stealth shape rather than flat rings out the side. It'll seem to have almost a sphere as it breaks the sound barrier. You'll see this a cloud form just briefly as it breaks the sound barrier in a spherical shape around a B-52 or not a B-52, a B-1 bomber, sorry, B-1, the stealth bomber. Now I don't want to talk forever. I think I've covered the basics. Oh no, I didn't. There's one more little thing I got to go into. So I'm up to 35 minutes. Well, could be worse. There gets to be a size where size becomes matter to us, and it's the tetrahedron I'm telling you is a gamma particle. Now, gamma particles are quite small compared to an electron. Where did I put that thing? Jeez. And I'm going to tell you, because I don't want to waste a whole lot of time, that an electron takes the shape. This isn't a very good icosahedron, but imagine this shape here with this shape on top. I'll get to this in a second. And there was another one of these things in the bottom. I'm telling you, oops, I have to get down here. I'm telling you that the electron takes the shape of an icosahedron, and it's constructed of 5 gamma particles, 10 gamma particles, and another 5 on the bottom. And together they form a shape which is 20 irregular tetrahedra. And another way of viewing them would be it's this shape here. When you take half of it, let's see if you're in the screen here. When you take half of it is Johnson solid, or no, the whole thing is Johnson solid J13, which is a dual pentagonal pyramid. So the top piece and the bottom pieces are pentagonal pyramids, and this is a dual pentagonal pyramid, which is Johnson solid J13. So I'm going to tell you, this is strictly my opinion, this is an X-ray particle. An X-ray particle is composed of 5 gamma particles of single tetrahedra each. That's as long as I don't change my mind. The gamma has to be just one single one. And this piece here, this neat looking Ferris wheel kind of sucker here, this is the center part of the icosahedron into which the Johnson solid J13 will fit. And another one on the other side to form the electron. This is serious matter to us, and it is so extremely stable that it governs all of our reality. We use electrons as the basis of quantum physics. We use it for everything. Seeing, hearing, television, nothing works without electrons. And all it's doing is churning the dark matter all around it as it spins. See, it's a very good little pumpy shape here. And it's a very good keystone shape for constructing long chains. You can see if you take this shape, you take this shape, are we on the screen here? If I take both these shapes, you can start constructing long chains of these things, which will turn out to be quarks. And there will be limits to different types of quarks. And then at some point they will join together and form lattices, which will become, did you notice how I was talking about, if you just observe the structure of the numbers and how big, if we look at the large atoms, which is going to tell us a lot about structure, that you start with a tetrahedron, then you start doubling the values and moving up. And then you've got room for the joints where these electrons fit into the whole scheme of things. There's a value, you can buy these magnetic ball bearings, and you can make I can't remember what it's called, a hecto-octag. You can make these torus shapes, which are fundamentally based around the number 5, which form a ring. And I'm suggesting to you that protons are really toroidal in shape, and at the very, very, very center of it, there's just enough room. Well, I didn't tell you what I think this is. This is a neutrino. This is the shape of a neutrino, and there's 3 kinds. The basic kind, a tau neutrino, where there's an X-ray attached, and there's another one where if you attach the whole electron to it, it would be an electron neutrino. And if you had a neutrino plus an electron plus another neutrino on the other side, you'd have a muon, but they decay really rapidly. I think 10 to the minus 5, so it's not very stable. You see muons in certain reactions. So a muon is just an electron with two neutrinos attached to either side. And these X-ray particles, they're really only stable as long as they're attached to something like a neutrino, or if they've got enough energy to have a crap load of spin. As long as they've got lots of spin, they're good. But if they lose their spin, it's going to depend on what's going around about them, if they can stay together or not. But so long as they've got spin, they have more energy than whatever it is around them. Once they stop having spin, they become a really serious solid and in danger of obeying the second law of thermodynamics and crumbling and coming apart. Okay, I think I said everything basic. I'm sure I missed a crap load of stuff while you're up. I have to get down here. I'm sure I missed a whole bunch of stuff, but very rapidly I wanted to just show you a way of structuring the universe from nothing. And you have to remember that there is no empty spaces, but pressures can determine the shape of something, and then all of whatever smaller dark matter, dark energy that's inside that shape has to obey Pascal's law, Pascal's principle. The pressure will be distributed equally within that shape, and the various shapes, by combining together, will enlarge the field, and together, because they're sharing a common pressure, and once they gain spin, they'll have even more energy than what's around them. That pressure will be distributed evenly within them, which is what will help them push back the pressures of gravity. Gravity is just the rest of the universe trying to crush you to nothingness. They don't want you, they don't need you, go away, just like the humans are. That's why I'm so reclusive. I'm not big on humans these days. But I won't get into that. I'm quite friendly. I think the humans just don't know enough. They're a danger to themselves and everyone around them. So now I'm going to go stop this recording, and I hope I got my point across. And I don't think I'll attempt to make a fourth video. This was my third attempt. Bye-bye, everybody.